So previously we've introduced the resistor and we've revisited Kirchhoff's laws. So now I'd like to apply those concepts to think about what happens if we have resistors in series. So let's have a battery hooked up to two resistors. Sorry, those resistors look awful. R1, R2. So we have two resistors in series. And again, we know they're in series because they pass the finger test. We can run our finger through both resistors and, in fact, through our battery here. And they never go through a junction anywhere. So the battery and both resistors are in series. Now, what I'd like to do is I would like to replace these two resistors with one resistor that does the same job. So this would be what we call the equivalent resistance to R1 and R2. So what do we mean by the same job? Well, from the perspective of the battery, all the battery knows is that it's shoving electrons around. And so as long as it keeps moving the same number of electrons through itself every second, then as far as the battery's concerned, it's the same thing. So let's go ahead and mark our current here. So we'll say that the current there is I. And if we're going to be doing the same job, the current here needs to be I. So remember, the current going through all of these elements has to be the same because there's no junction where any current could split off. So whatever passes through the battery has to pass through each of the resistors in turn, and around they go. So we can go ahead and write down Kirchhoff loop laws for both of these systems. So for this one here, I'll start the lower right-hand corner and go around clockwise. So as I walk my dog along, I go through the battery and leave at the positive terminal. So I would write in E. And then I would pass through the resistor in the direction of assigned current because we're saying the current is going clockwise. That would be down. It means we're going with the current here. So we'd write minus IR1 minus IR2, and then I get my imaginary dog back home, and I write equals 0. If I repeat that for this loop here, this is going to be E, and then going through here, I'm going with the current, so minus I R equivalent equals 0. Okay. So let's rearrange these. So we have the EMF here is equal to I R1 plus I R2. And here we have the EMF is equal to I R equivalent. Well, two things equal the same thing are equal to each other. So let's set them equal to each other. I R equivalent is equal to I R1 plus I R2. So we can cancel the currents. So we're left with R equivalent equals R1 plus R2. And if you had more than two in series, you would just keep adding them. So R1 plus R2 plus and such up to Rn. And so you'll note that this rule has the exact opposite functional form as when we were putting capacitors in series. So here we add the resistances. So as a sanity check, if your resistors are in series, the equivalent resistance should be greater than the largest resistor in the network. All right. So in this picture that you see here, you can see that I've hooked up a couple of batteries in series. That's just so we get a 3-volt potential difference. And I have hooked up a single light bulb to the battery. And you can see that lights up. So now what I would like you to imagine is, and just in case it's not clear, the red leads are connected to the positive terminal of the battery, and the black leads are connected to the negative terminal of the battery. Now, what I would like you to imagine here is what would happen if, instead of having one light bulb connected to the battery, I have 2 light bulbs connected to the battery in series, much like our 2 resistors in series that we were just looking at. I would like you to predict how will the brightness of the lights compare to when we have just a single bulb. And I would also like you to predict how the brightness of the bulb that will be hooked up to the positive side of the battery compares to the brightness of the bulb hooked up to the negative side of the battery. So go ahead and pause the video making your predictions, and when you're ready, you can resume. Okay, and so we can see in this picture that both bulbs are substantially dimmer. In fact, they are 1/4 as bright, and they don't even look that bright to our eyes because the spectrum of the light shifted deeper into the infrared. But if we had eyes that could see in the infrared, we'd say, yeah, they're 1/4 as bright. And it looks like the 2 bulbs are the same brightness, and that is also correct. And this makes sense because, remember, if they're identical bulbs, whatever current goes through the one bulb goes through the other. The brightness of the bulb is going to be proportional to the power, and we saw that the power is going to go as the square of the current. All right, so now what I would like you to imagine is what would happen to the right-hand bulb if I unscrewed the left-hand bulb and remove it, but otherwise leave everything hooked up. So again, pause the video and resume when you're ready. Okay, so from the video, from this picture, we can see that the right bulb is out. All right, now let's go ahead and repeat the same thought experiment, but instead of unscrewing the left bulb, we unscrew the right bulb. What will happen to the brightness of the left bulb? So go ahead and pause the video again. All right, and we can see from this picture that, again, the bulb is out. And this makes sense because if I unscrew either bulb, what I've done is broken the circuit. And so then there's no way for charges to move through the circuit, so the battery just doesn't shove any charges along. Alrighty. There's actually a fun application to this that shows up. If you've ever gotten a string of newer holiday lights or party lights, not the kind that are the LED bulbs, but just the cheaper ones that still have teeny tiny incandescent light bulbs in them. And again, I'm not talking like the kind that you get from your grandmother's closet where they had really big bulbs. Those worked differently. So it turns out that in order to save on copper, because copper is kind of pricey, so in order to keep unit costs down, when these bulbs are, when these party light strings are designed, they are actually wired up in series. which leads to a problem. What if one bulb burns out? If one bulb burns out, then the whole string goes out, as we've just seen. So there's actually a really clever solution to this. There's a little device sitting, put into these light bulbs, sitting right at the base of the bulb. So I'm going to try to draw one of these party lights, and I'm really sorry. Yeah, maybe something like this. So it goes like this, and you'll have your filament here. If you look very carefully at the near the base of the bulb, you'll see there's a little thing sitting right here. This is called a shunt, and normally it's not electrically connected. But if the bulb burns out, the filament will break, and when the filament breaks, it activates the shunt electrically, so that current, instead of flowing through the filament, will now flow through the shunt in order to maintain the electrical connection. So if you've ever read the owner's manual that came with your party light string, and yes, I did, mostly out of the pure fascination that there was an owner's manual that came with it. It was printed on 1/4 of one sheet of paper. It did very carefully say that if a bulb burns out, that you need to go through and immediately find which bulb burnt out and replace it. So let's say you are less than zealous in doing that, and you have a few bulbs burn out, and you decide that's not a big deal, and you go ahead and leave your party lights up, and then suddenly what you'll probably start to notice what happens is that all of a sudden a few more bulbs go out, and then a few more, and then a few more, and then like all of a sudden the last half of the string seems to go out almost all at once, and now you've fried every single bulb in the string. So using what we know now about the anatomy of these bulbs, I would like you to pause the video and think about why it is that this happens. And when you're ready, go ahead and resume the video, and we'll see what we come up with. Okay, so although it's technically AC, we can still think of it as being wired to a battery in DC for now. So let's say we've got a bunch of bulbs in series like this, and our bulbs are acting like resistors. And let's say one of them fries and the shunt activates. So in that case, what happened to the overall resistance of the circuit? Right, the resistance went down. So if the resistance of the circuit went down, what happened to the current going through the circuit? Right, it went up, because twinkle, twinkle, little star, delta V equals I times R. So the voltage is fixed by the battery EMF. So if the resistance of the circuit goes down, the current will go up once the shunt activates. So if the current goes up, what does that mean for the amount of power that each of the remaining light bulbs is radiating? Yeah, they go up. In fact, they go up quite a bit, because remember, the power being radiated goes as the square of the current. So they're dissipating more heat more quickly, which means the temperature of the bulb is going up and you're increasing the probability of melting another filament. So then let's say you do melt another filament, let's say it was that one, and again the shunt activates. Again, it'll be the same deal. The resistance will go down, the current will go up, the power being radiated by all of these, by the remaining bulbs, is individually going up. And so the bulbs get hotter, and then you're more likely to melt another filament, and so forth and so forth. So that is why you really do need to stay on top of it. Or you can do what I did and decide that it was worth spending the extra pennies on a string of LED bulbs. Alrighty, so let's just do one example with numbers just to make this concrete. So let's say you have a network of resistors here. Let's say this one is 2 ohms. And it's in series with a 3 ohm resistor and let's say a 6 ohm resistor. What's the equivalent resistance of this network? Well, you just add them up. The equivalent resistance of a series network of resistors is just the sum of all the resistances. So this will be 2 ohms plus 3 ohms plus 6 ohms is 11 ohms. All right. So in the next video, we will tackle parallel resistors and more complicated networks that can be viewed as combinations of series and parallel. So see you in the next video.